We're going to talk about one-sided limits. So far we've been looking at limits from, the limit exists if it's the same from both the right and the left. Okay? Well, now we're actually going to define what a right-hand limit is and what a left-hand limit is. Okay? So, I have two limits here. What I want you to notice is this symbol right here, and I know that's why I'm highlighting it for you. Okay? If you see the limit as x approaches a value with a little negative as a superscript, that means we're looking at the left-hand limit. So what are we approaching just from the left side? Okay?
So this is getting rid of one of our gains.
Well, this is saying we can look at the left and right separately and say what?
Oh.
Yes. Okay, so hold that thought real quick.
So negative is what?
Right, because those x values are smaller on the left, and so that's why it's a negative. On the right of a number, those x values are bigger, so we notate that with the positive. Okay? So here is a left-hand limit. This is a right-hand limit. Okay? Now, Zach said something about, well, this is going to take care of some of those D and E's. Okay, you're going to be able to find a right-hand limit most of the time. You're going to be able to find a left-hand limit most of the time. But what's going to be true if our right-hand and left-hand limits are not the same? Then the limit won't exist. Okay, but we can look at right and left hand separately now, and we have notation for that. Okay, so the first thing I want to talk about is direct substitution. Okay, is everyone good for me to go on to some direct substitution? Okay, so you might get some problems that look like this. Bigger for you. Okay. The limit as x approaches 1 from the left of 4x squared minus 5. Now, we have the same thing with direct substitution. Okay. If we're not at like a break or a hole or an asymptote or anything like that, we can just plug 1 in. Okay. So even though we're just looking at the left-hand limit, since this is a nice smooth curve with no holes or gaps or anything like that, we can just say that the limit is -1. Okay? We can think about this graph, 4x squared minus 5. So we're shifted 1, 2, 3, 4, down 5 with a vertical stretch. Okay, from the left side, we're approaching the y value of -1. Okay. What about this limit right here? Okay, so the limit as x approaches -2 from the right side. If we use direct substitution, what would it be? Where to 0? Because the graph looks like this. No, it doesn't. That's not what it looks like. What does that graph look like? It's a semicircle, isn't it? Yeah. Okay. So if we look at -2, here's -2 right here. From the right side, our limit is 0.
Wouldn't that be from like the left side though?
This is from the right side.
That's the left side.
It's the left side of the zero.
It's the left side of negative 2.
Oh, so.
Or, excuse me, the right side of negative 2.
Alright,
Okay? Does this have a left-hand limit?
It'd be,
No.
Because there's nothing to the left of negative 2, so there is no left-hand limit. We only have a right-hand limit.
But what about on the other side?
So this would only have a left-hand limit.
Oh, you're talking about the specific point. I thought you were talking about.
Yeah, because this is negative 2. So here's negative 2. X is negative 2. We only have graph to the right of it. So we have a right-hand limit. Okay. All right, let's look at some graphs. Because really when I ask you for one-sided limits, graphs are going to be the most important. Okay? Here's our graph. If I ask you for the limit as x approaches negative 1 from the right. Okay, so here's x is negative 1. From the right, we're approaching 1. Okay, what about the limit as x approaches negative 1 from the left? Okay, from the left side of negative 1, we're approaching this coordinate right here at 2. So let me ask you this. What is the limit as x approaches 1? Does not exist because the right hand and the left hand limit are not the same.
Well, what's your line?
Oh, I'm sorry. I went negative 1. I had a nice little setup going there. I didn't even follow it. Sorry. But it's true at positive 1 for the same, right? Okay, what about the limit as x approaches 2 from the left? Two from the left. What about the limit as x approaches 2 from the right? 2. So the limit as x approaches 2 is 2. Okay, see how that works?
That only works with like in those kind of graphs, I guess, right and left side.
Well, as long as the right and left hand have the same limits, then your limit exists. Okay? Last one, the limit as x approaches 3 from the left. Could we evaluate a right-hand limit there? No, we could not. Excellent.
what would it be meaning?
Right, it doesn't exist because there's nothing there. Okay. Next kind of problem you're going to see looks like this. What kind of function do we have here? A piecewise function. We have 2 different pieces. Okay? So if you have the limit of a piecewise function, we still do direct substitution. However, if I ask you for the limit at the breaking point, we have to be careful. Anytime I ask you for a limit at the break in the domain, you must use left and right hand limits. Is that okay? So first, the limit as x approaches 0 from the left. Which piece is to the left of 0? This first one, right? So if we plug 0 into that first piece, we get 1. Okay? Now, we can look at the limit as x approaches 0 from the right. Which piece would we need to use direct substitution with? The second one, because this is to the right of 0. Okay? And what is that limit? 1. So our left-hand limit is 1. Our right-hand limit is 1. So the limit as x approaches 0 of h of x is 1. If you have a piecewise function Where the limit is being evaluated at the break in the domain, I have to see this work or you get no credit. I know you can do it in your head, but I need to see with my eyes that you took the right hand and the left hand limit.
So is this just like
Well, it's checking your work, but writing it down, okay? Now here's the graph, okay? So we have a line and a parabola, okay? The right hand limit is 0, or excuse me, 1. The left hand limit is 1. This limit exists because they're overlapping at that point, right? They're connected there. There's not a jump. Okay? So if these two were different, we would see a break in our graph, and what would we put for the limit? Does not exist.
So you can have like a limit that doesn't exist, but still have lots of right hand limits.
Right. Like this one. I told you to remember what this graph looks like. Can anybody show me with their arms?
I can't get my hands that wide. Doesn't work.
Let's look back.
Oh.
Oh,
Okay, remember, y equals absolute value of x over x, okay? You're either taking x divided by x or negative x divided by x. So you're either getting 1 or negative 1. You see what I mean there?
Yeah.
This minus 5 in each just makes it shift to the right 5. Okay? So if you didn't write it down the first time, you may want to write down what this graph looks like. X divided by x, we get 1. X divided by negative x, we get negative 1. Okay? So, struggling. Oh, I'm struggling. There we go. What is the limit as x approaches 5 from the left? Negative 1. What's the limit as x approaches 5 from the right?
One.
Positive 1. So what does it mean about the limit as x approaches 5? It doesn't exist. Okay? I'd like you guys to remember this graph. It will help you when you see a problem like this, where you have the limit as x approaches something with the absolute value over x. Okay? Anything that's set up in this fashion, I want you to remember the graph and think about the right and left hand limits.
So using the parent function, how does it get translated? I'm guessing that the minus 5 means that it moves right 5, but how would you move it vertically, and how would you expand it?
Vertically would look like that.
And like, how do you widen it vertically? Would that just be a multiplication?
Yeah. Yeah. Really, you're probably just going to see like x plus 3, the absolute value of x plus 3 over x plus 3. Or, like, it's probably just going to be a horizontal shift is what you're going to see.
Are we always going to get the graphs on those then?
No. That's why I said you need to learn that graph.
How would we do that vertically?
Like this. I want you to just think about the graph. That's why I'm telling you how to do this. Okay?
Is it always going to get 1 and 2?
Unless there's like a 2 in front of there. Then it'd be at 2 and negative 2. Okay. What? Well, I want to see that you're thinking about the left hand and right hand limit. Yeah. I'd like to see that. First of all, factor it. And what can happen? So I have the limit as x approaches 1 of g of x. What's our limit? what's our limit? 2. Do we need to do left and right hand limits here? We wouldn't need to break it apart, okay? What's happening graphically? We have a hole there. We have the line x plus 1 with a hole at 1, 2. You would not need to algebraically look at the right and left hand limit because we have this strategy that is much more efficient, right? Because we're left with x plus 1. So when we plug 1, okay, 1 makes our denominator 0 originally. In our reduced function, when we plug 1 in, we get 1, 2. And so that is where our hole is.
So you reduce and then you use the reduced function limits?
Mm-hmm. Yep, just like we did in our homework Friday night.
Wait, so on the piece-size ones, you plug it in, on these ones, you just have to know the graph.
On this one, we did everything algebraically. We don't need the graph. We have a rational function. We could reduce it. Once it's been reduced, we can use direct substitution. Okay? Anytime you have a rational function, see if it can be reduced. Okay? It will help. Okay, anytime you have a rational function, factor and see if you can reduce, and then see about evaluating your limit. So at first, plugging 1 in to the denominator made that denominator 0. But then when we reduced it, we can just use direct substitution. Okay, this is just a problem from a couple days ago that I put in here so you wouldn't forget our strategies. Okay? Just because we're talking about right and left hand limits for these next few minutes doesn't mean that we can forget what we did a couple days ago. Okay? Yes, we can look at the right hand limits and the left hand limit, but we don't need to on this one. Okay? Okay. I'm going to give you 2 minutes for you and your pod to work on this one. I'm giving you the limit of a piecewise function. What is true about the value of the limit?
Equals where it is.
Okay, this x value is where your piecewise function breaks. Go. So Abby, you need to go back to my videos and watch the example. Okay. We have a yeah.
So you plug it
Okay.
in.
Always look it over. I don't know.
I've done that twice before.
Are you done? Pod 5, are you finished? Problem.
What's up, Gina?
Pod 1, represented by Jimmy.
Oh, scary.
Like show all my work?
Agree so far?
Yeah. Yes. Oh, Jim, you need to look.
All right, here is Jimmy's work. He has a left-hand limit where he plugs 1 into the top function to get a left-hand limit of 2. We have a right-hand limit where he plugs 1 into the second function to get a right-hand limit of 2. And so then he wrote, the limit as x approaches 1 is 2. This work is beautiful. This is what I would want to see on tomorrow's quiz. Yes.
Is like the stuff up top on the piecewise function, is that always gonna be like the limit to the left?
What?
Yeah,
Okay,
the
so
limit to the-
so this is
Asking
saying
you
x
for
is
thought.
less than 1.
Yeah.
So when we looked at the left-hand limit, we looked at this piece because this is where we are left of 1. Does that part of focus? Does that make sense?
Yeah.
Okay. You aren't the only one with that question. I am sure. Okay. Yes.
This is a question about piecewise functions in general. Is the ones further to the left normally on top, or the ones further to the right are closer to the bottom?
They will typically organize these pieces as like the domain negative infinity to infinity, so that the smaller x's and then get bigger.
Yeah.
Yes.
Okay, that makes sense.
We could get one question. Negative 1 is less than x, which is less than 1.
Like a piece, like a three piece piecewise function.
Yeah.
That's possible. Yeah. But you just look at
We'll look at
the break in the domain and look at which piece you need.
So that gives you an x.
I think it's just a piecewise. What would look, this graph? So x plus 1. So plus 1. Oops.
I just didn't know if there would be a hole at the first piece.
No, because they overlap there. Since they overlap, there is a hole, but then it's colored in with the other piece. Okay. Okay, so this is what I want you to do. This is your homework to work on tomorrow. Like after the quiz.
Don't do it now.
Don't do it now.